Okay, so this talk is going to be about particulate flows, flows where there's turbulence and there's particles, but don't get worried, it's much more simple than these examples show here. So we're going to talk about very, very small particles which are in a flow. So the particle velocity, we'll call it V, and the fluid velocity, we'll call it U, and Q is going to be the difference. We can write the Navier-Stokes equations in the particle frame of reference moving with V, and this is what we get. So basically in the particle frame of reference, the Reynolds number of the particle is going to be much, much less than 1. A is the radius of the particle. Today we'll only be talking about spherical particles, and nu is the kinematic viscosity. So this Reynolds number is very, very much less than 1, whereas the Stokes number need not be. It could be much bigger than the Reynolds number. So such particles in such flows are said to be in unsteady Stokes flow, and that's what we're going to talk about today. So for unsteady Stokes flow, when you have a spherical particle and let's say it's in the middle of nowhere, like it's alone in a fluid and not interacting with any other particle, and when we ignore all kinds of higher order corrections and when we ignore gravity, we can write down a simplified form of the equation for this unsteady Stokes flow of the particle, which is known as the Maxi-Reilly equation. So Q is the quantity which represents the difference between the particle and flow velocity, as I told you, and this is what the Maxi-Reilly equation looks like. So this is just for one tiny spherical particle in this big turbulent flow, where you saw in particulate flows you could have quadrillions of such particles. So imagine you have to solve this hugely complicated equation for the dynamics of every single particle in such a flow. So now when you look at this equation and you see these pink terms, you see that there is a 1 over square root of t multiplied by the initial condition, and then there is this horrible looking integral. So you can imagine that in order to find the acceleration of the particle, I need to know its acceleration and the fluid's acceleration at every time in the past, and I have to integrate it at every time anew. So I have to start again from time equal to 0 because of this kernel, the square root kernel. I have to keep doing this integral every single time. Now what do we think of as a dynamical system? In a dynamical system I have, like let's say, some variations in time x dot equal to ax. That's the kind of equation we are used to, right? We're not used to something where the right hand side depends on everything in the past, like every past time. So we are used to something which is local in time, normally in a dynamical system, whereas this is not local in time. So like none of the simple things that we can apply seem possible here. It looks as if we'll have to do heavy duty computation every time, and we'll talk about this a bit more as we go along. This force is called the Bassett-Boussinesq history force. Okay, so it is usually dropped. And in the first part of this talk, we're going to drop it, and we're going to see what interesting things particles bring. In that way, I've changed the emphasis of my talk a little. Now, what happens in turbulence when there are particles? So, like here is a snapshot of 2D turbulence with vorticity, that is the curl of the velocity vector shown here. So you see that there are concentrated patches of vorticity in 2 dimensions. In 3 dimensions also there are concentrated, rolls or sheets of vorticity. So turbulence consists of a whole bunch of vortices, places where the curl of the velocity vector is high. So then what happens to particles which are in this flow? So normally, like what do we think of turbulence? We think of turbulence as a mixing agent, right? Like I put sugar in my tea and then I mix it, and turbulence always mixes everything. Turbulence demixes particles. So that's the first thing we should, turbulence demixes particles which are heavier than the flow. So let's look at that here. So I'll show you a movie here about what normally happens in turbulence. These are vorticities and these are particles. So this movie was made by Jason. You just see immediately that the vertical regions are evacuated by the particles, and these particles are collecting in the regions in between the vertical regions. So this is what is happening. And we can calculate many things exactly for a single vortex for heavy particles. So you see like there is this vortex particles are evacuating quickly from that neighborhood. So you can actually compute the void region and so on. And once you know the void region, you can check how much void there is in a typical turbulent flow. So given a particular Reynolds number, you can ask how many particles will collide with who all. And this collision is very, very important for many situations. So sometimes like raindrops with each other and that makes them coalesce. So the occurrence of rain is very dependent on this kind of thing. That's just one example, but we can calculate everything if we know this void volume. So now we're going to question this or ask whether this always happens. So this is the thing. So the dogma in turbulent flow is that particles evacuate vortex neighborhoods and collect in regions of strain. So this is the dogma that we are going to question in some sense. So we are trying to counter the dogma. We are saying there is more to it than just voids near vortices. So don't think of particulate flows as just particles centrifuging out of rotating regions and collecting in the voids. Let's see what else can happen. The first point to notice is that vortices are everywhere, whether it's in 2D turbulence or 3D turbulence, and they interact with each other. They tell each other how to move. So what happens when vortices are interacting with each other? Two particles. So this is the question we are asking. And what's the simplest thing we can do? We can take two vortices which are interacting with each other. So that's what a lot of this talk is going to be about. So we start with two identical vortices in 2 dimensions, and these are those two vortices. They have a circulation gamma, where gamma is just the integral of the vorticity across this area. So these are two concentrated, you can think of them as endless rods of vorticity, and what each vortex will do to the other, and we are going to be putting the vortices in an inviscid setup to make our life easy. So they are now, and what will happen is this vortex will put a induced velocity on that vortex, which will be gamma by 2 pi d, where d is the distance. This vortex will do the same to the other one. So like they will keep rotating like this. They'll keep going around and round in a circle. So this is the simplest interacting vortex system that we can have. And now like, think that any self-respecting particle would just centrifuge out of this entire neighborhood, right? When there are two vortices. It was, they were centrifuging out of one, so they should centrifuge out of 2, 3, whatever is there in a bundle. So that's the question we're asking. Now we are going to be living in this co-rotating frame. We're going to be co-rotating with the vortices, so we'll always see the vortices sitting here. So the equations and everything we're going to be writing with, this is basically the frequency with which these vortices rotate around each other. Now, in that co-rotating frame, what happens to passive particles? So suppose I put particles in this flow which just go with the flow velocity, that's all. They're just very tiny passive particles. These passive, so here are the vortices, because remember I'm in a co-rotating frame. So these two center things are always going to be the vortices. And this picture is going to recur several times in this talk, so please look at it a little bit. So all these black lines, they represent camptori. So if I start a particle here, it will stay forever here and keep going round. If I start a particle here, it will stay forever on that. So there's a whole bunch of camptori which are inside each other, and so there's a saddle point here, but particles keep going here. So like this is the kind of trajectory that each particle is going to adopt when you have two vortices. So these are about passive particles. Now what if I put heavy particles? So our first conjecture was that they will race out of this entire space, right? Which didn't happen, which doesn't happen, which is why I'm standing here. So like we have the equation, the Maxi-Reilly with the Bassett term ignored. We write it in the co-rotating frame and it looks like this. There are two important parameters here. One is the density ratio, like how dense is the particle compared to the fluid, and it's given in inverse form in this quantity R, where R equal to 1 means the particle and fluid have the exact same density, and R equal to 0 means the particle is infinitely heavy compared to the fluid. So this is the density ratio R. And then there is this quantity called the Stokes number. Remember I told you A is the size of the particle. So basically, as you make the particle larger for the same density, I can have different Stokes numbers. And what does the Stokes number represent? It represents the inertia of the particle. It represents the reluctance of this particle to follow the flow. So if the passive particle, Stokes number was 0. So like if the particle becomes higher and higher in Stokes number, it will follow the flow but reluctantly, and there will be a response time which scales as the Stokes number. So basically that's the Stokes number and that's the density ratio. So these two are going to be our important parameters. So first let's consider heavy particles where R equal to 0. Heavy particles, small Stokes. Already you see a big difference. Earlier it was cam tori, right? Instead of cam tori, you are getting attracting fixed points up and down. So this thing which was a cam torus over here, let's look at that one because we are doing the top, has become this and this has become this. So anybody starting anywhere here in this red region is going to go in and cluster there. What does that mean? That means that a lot of droplets are going to come very close to each other and there's going to be lots and lots of collisions, coalescence, interesting things are going to happen here. So that is very interesting for turbulent flow. So instead of cam tori, you got them converted to attracting fixed points. Note that these are moving fixed points in the sense that my entire coordinate frame is rotating. So this fixed point is not fixed in lab space, it's actually rotating like that. So particles are clustering there and rotating like that. So that is basically this. And these are the basins of attraction to those attracting fixed points. So we keep increasing Stokes number bit by bit, and you will see that earlier at very, very small Stokes number, almost everybody here gets attracted to that fixed point. So very large number of particles are clustering at one place. As you increase the Stokes number, this basin of attraction keeps going down. And after a certain Stokes number, that means slightly more inertial and bigger particles, they're going to leave the vicinity of these vortices. So they're going to do exactly what we expected earlier, but at small Stokes number that is actually not the case and something quite counterintuitive is happening. So like we saw that these cam tori got converted to attracting fixed points. For heavy particles, that means particles which are much, much heavier than the fluid, and as we had low Stokes number. So like, does the story finish here? Like, is that all the interesting thing there can be? So what happens if we'll change the density ratio? What happens if we make the particles lighter and lighter than the heaviest and come towards the fluid? We'll never go lighter than the fluid, but what if we make them more and more comparable? So if you think of little plankton which are sinking in the ocean, those things have comparable density to the fluid. And also microplastics and stuff like that. So like, what if we bring the density to those levels? So the instinct may tell you that, okay, the basin of attraction may change a little bit and maybe it can stay, you know, for a bigger Stokes number in the vicinity. You can make guesses like that. But nothing prepared us for what we found, which is that, and here is one particular density ratio, which I told you both of these are kind of comparable. This is 1.3 times and this is like 2.5 times the density of the fluid. So different Stokes numbers, those attracting fixed points went through a half bifurcation. You started getting limit cycles. These are three examples where here there's a limit cycle of winding number 2. Here there's a limit cycle of winding number 4 for a small change in Stokes number, and then a winding number of many, and this is followed very quickly by a strange attractor which is chaotic. So like, you're seeing these, there's actually the whole thing behind, but it's so light you can't actually see it. The whole structure is, you know, the cam tori and things are shown there and the vortex is here. That you can't see, I'm sorry about that. And these are the basins of attraction just shown for another density. So like, let's just say these are 6 examples in the Stokes number density ratio plane. We've taken 6 examples where we saw different kinds of behavior. So like, our next job is to say, okay, let's populate the entire plane and see what are the different kinds of behavior that you can get with Stokes number and density ratio. And that is shown in this. So this represents the winding number, where winding number, this one is 2, like you went through 2 cycles before you came back to your old position, and here the winding number is 4 and so on. So that winding number is shown in color in this, and in the black region you have attracting fixed points. So like this limit, the heavy particle limit, we saw that up to a very tiny Stokes number you had attracting fixed points, and after that nothing. This is what we'd seen for heavy particles, and now we're going lighter and lighter in this direction until at this place it's neutrally buoyant. So the interesting thing is you have like a 1 cycle, 2 cycle, these are like just a limit cycle with 1 in it, and this is 2, the winding number is 2, 3, 4, and like the red part goes very quickly to chaos. So already you see it's not monotonic, it's not anything you could have ever predicted. So this actually shows that if you have particles of finite density in a fluid, just in the presence of 2 vortices, the simplest toy problem of interacting vortices, already like many very interesting things can happen. So the dogma of leave the vortical region is not quite correct over here. So like here we look at 3 particular places. This is one, this is a simple case where it goes from 1 cycle, 2 cycle, 4 cycle, etc. to chaos. And then the chaos ends. So this is going to be an easy case where the density ratio is 0.84. The next case we're going to look at is here, which is like hugely complicated. So it's going through these things, then to chaos, then to attracting fixed points, and then to chaos again, and so on. So many things are happening in this. And the third one like never goes through chaos, but it goes through some period doubling and goes back to nothing. So we'll be following like some parts of these lines in the next slide. So the first case where 0.84, it's a very traditional bifurcation diagram. And in this bifurcation diagram, we have plotted all these extrema in X. So 1, 2, 3 and 4 would be for this one. So this is a traditional bifurcation diagram, and it obeys Feigenbaum ratio and everything, and the Stokes number for chaos is 0.2455. So it's interesting that these are particles trapped in the vicinity of a vortex, but they never repeat themselves. They are in a chaotic orbit. So this is what happens at that density ratio. The next density ratio, it goes through a period doubling route, period doubling of the limit cycles, not fixed points, and then it goes to chaos, and then the chaos dies away and it goes back to attracting fixed points. And this is at the other density ratio where there is no chaos, but you see very interesting bifurcation followed by upside down bifurcation. Now we looked at the residence time. So this is kind of remarkable. So you put particles in the vicinity of the vortices and you ask how long will they live there, and this number is the log base 10 of the number of vortex cycles. That's going to be like way bigger than the vortex lifetime itself. So like this is how long the particles are going to be tied to the vortex. It's really remarkable. So in these ratios, so again it's something very interesting which you couldn't predict in these 2 numbers, and more fun than that is that at even very high Stokes numbers there's a particular density ratio where you see non-trivial behavior. And this is like just to show that there is a logarithmic behavior in residence times, and this is the kind of beyond the chaotic place what happens. So you see how particles leave this thing and how long they're going to stay, and you see interesting patterns over there. So now till now we'd ignored the Bassett history. We pretended it's a dynamical system. We're going to stop ignoring it now and see what it brings. And the same worry I'll remind you, and this work was done initially by Ganga Prasad, who's there, who's now a faculty member over here in IIT Madras, and Divya, like she is a present student, amazing one who's doing a lot of the work on this, and Vishal Vasan, my colleague, who's the brain behind this part of the work. So basically we ask what we can do to this thing which doesn't look like a dynamical system. In fact, after I wrote the title and all, I was thinking I should have actually called it not a dynamical system which isn't actually one, but a non-dynamical system which could be one. So that would have been a better title, so please read that as a given. So then the interesting thing is that this whole thing, the Bassett history, you can think of it, it's actually a half derivative in time. It's a fractional derivative in time. And so if you write a fictional heat equation like this, a half derivative in time becomes a full derivative in x. So I could write it as qx goes as all this. And so like in this Maxi-Reilly equation, I now replace it by a q, which is like the first derivative in this fictional variable x. And the whole Maxi-Reilly equation looks like this. It basically sits on the boundary of this. So the entire history is encoded in some Fourier modes. So how does that work? I will skip this whole thing in the interest of time, but the point is that we write down a thing called a history variable. We write a history variable which contains all the Fourier modes in this fictional variable x, and it looks like this. It's given this form, and you can actually like do a whole bunch of algebra and come up with an equation h dot plus something something equal to something. So this thing, you can write it in this form. Okay, I wrote this a bit shoddily, but finally we can write it as a dynamical system which is much bigger than the old one. So we're writing it as this is a complicated nonlinear function of v and h. That's what I meant by this right hand side. So we can actually write it in this very elaborate way as a dynamical system. And the nice thing is that you don't need infinite k's, you need only a few Fourier modes, and you can actually represent the system, because any physical system, when the k becomes too high, like those modes are usually killed off by viscosity in fluid mechs. So we actually end up with a few modes of h, and we can solve this dynamical system exactly. So now that we know how to solve it exactly, like if I did it by brute force, this is actually a bad plot. We have like plots which look even more dramatic. Our method works in much shorter time. It uses much less computational memory. There's also one more very interesting thing which happens here, which is that, because our system has these square roots of time, we can't write it in a normal Range-Kutta. Like, when you look at a dynamical system, you want to write it in higher and higher orders of accuracy in time, right? Like do Range-Kutta and things like that. But imagine any function which doesn't go as a Taylor series. So it goes as square root of t to the 2/3, 3/2, and so on. Then you have to write a more imaginative Range-Kutta for that, and that's what Divya did. She's simply amazing. And so we can do that, and so we can actually, we're now in a position to solve a whole bunch of numerical things with that. And the nice thing is that now that we write it in terms of this history, we can actually get analytical solutions. So this is, for example, for a particle in shear flow. So for two different density ratios of particle to fluid, you see that when it's very, very dense, history doesn't make too much difference. But when it's comparable density, then history makes a lot of difference. So this thing, the movie started playing, but basically what we did is we kept a vortex here and we put a particle necklace. So imagine there's a vortex like this and there's a long line of particles like this. And then we asked what happens to that particle necklace, and the color is like, the color basically shows the initial position of the particles, and we've done it with and without history, and we've computed the collisions. So where all do collisions happen and how many? So you see already quite a bit of difference between Bassett and no Bassett. This is like for a very small density ratio, and you see that just with one vortex you get pretty interesting dynamics of the particles. So this is in the VR plane. That means when V is negative, that means a particle is going inwards, not outwards. So you have something which should be centrifuging, which is actually spending some time inside because of its initial condition. And you can see that Bassett and no Bassett are indeed somewhat different. So this tells us that all the results I showed you for the two vortex case, which I'm excited about because we got them like just a few days ago, but we have to repeat them with the Bassett history included. And so this is basically the summary of my talk. The first thing is, counterintuitively, huge amounts of clustering near vortices is possible, and we've seen this just from two vortices which are identical. We have to study a whole range of vortices to see how much time particles can spend just because the vortices are interacting with each other. And you know, the two important parameters, the Stokes number and the density ratio, the behavior as it depends on them is rather rich, non-monotonic and somewhat unpredictable, like we couldn't have guessed at this. And Bassett history needs to be studied, and though I say it myself, the new approach is nice. Thanks for your attention.
Thank you very much. Is there any questions or comments? Yes, please. Is the dependence not like fractional differential equation?
Yes, you end up with a fractional differential equation. And that's what we did. We recognized and converted it to a partial differential equation. It's kind of interesting because like here is an ODE which we're converting to a partial differential equation to make it simpler. Normally you do the reverse.
So the fixed point becomes more stable?
The fixed point, no, we can't say that. We've not done it with the Bassett history, so it could become more or less stable. Everything is counterintuitive over here.
Rama, you said that there were cam tori. Cam tori happen in Hamiltonian systems. So what is the conserved quantity here?
So this is actually a Hamiltonian system. The energy is conserved. The two vortices are going round and round, and they're generating the exact same velocity everywhere. The velocity is going down as 1 over r, broadly as 1 over r. So this is a Hamiltonian system.
But it's Hamiltonian in how many dimensions? I mean, see, the energy is conserved, but there's something else which also seems to be conserved, right?
What else is conserved? It's okay. So basically, as far as the two vortices are concerned, they're actually static, like in the co-rotating frame.
Yeah.
Nothing else is happening to them.
Right.
So like there's no dynamics of the vortices themselves in this frame. You put particles in that frame and you ask how the particles go. And that's what these cam tori are representing. So in each of them there is something conserved. So like if you look at the time it takes to go around, everything is according to what you'll expect from Hamiltonian dynamics.
I see. No, okay, so the other point is that outside the cam tori something is not conserved. So what is that which is not conserved there?
Okay, there is nothing except cam tori in this. Outside this big circle, the particles are just going like that. They're just passively deviating a bit, but they're going far away. So like these are the trapped particles. Everything that's inside this big circle is trapped and everything outside is not trapped. That's all that is happening.
The T-junction problem where you have like bubbles moving into a T-junction flow and getting trapped in the vortex bubbles. Bubble means that's less dense compared to the ambient fluid.
Yeah.
So it seems like the work that you have done is relevant to explain that as well. Am I correct?
Okay. So like, when I said that heavy particles leave the region of the vortex, they just spiral out because of centrifugal force. Light particles are going to go in.
That's exactly what is happening.
So bubbles will go and get trapped inside vortices. So when bubbles or anything, when the density is less than that of the fluid gets trapped, we're never surprised. It's when something is heavier than the fluid but still gets trapped. That's when we're surprised. And here we have like infinitely heavy particles where R was 0. They were getting trapped. So that was what was surprising.
And do you think the history force is going to be important to understand the details of the mechanics there too?
The history force is going to be important in some region of that parameter space. It won't be important everywhere.
Thanks.
So we still have to explore that and work out where it's important. In particular, when the densities are comparable, it's going to be important. That's our guess.
There is something I quite have not understood, because you are talking about Cantor-I, at the same time you are talking about attractors.
Yes.
Hamiltonian systems do not have attractors.
Very good point. I should have made that clear. So this is with passive particles. The minute you put inertia into particles, like we've done here, there's a Stokes drag over here,
Exactly.
they become dissipative.
Exactly,
So
that's
this
the
is
point.
a dissipative system for any non-zero
Yeah,
Stokes number. And that's why,
and the
like,
Cantor-I became destroyed.
yeah, they got destroyed and now you got attracting fixed points.
Okay.
Yeah, Rama, I just wanted to say that Nirmal Tyagu and I many years ago had in fact worked with embedding maps, and we had seen somewhat similar effects to the clustering that you are seeing.
Okay, I'd like to talk to you later about it.
So, in the example you shown that strength of both the vortices are the same, right? So if you change the different strength, will the dynamics be similar?
I cannot guess, but the dynamics will somewhat be different because whenever the strengths are different, one vortex becomes a satellite of the other.
Oh, I see.
So like
Yeah.
different things can happen, but still there is a co-rotating frame in which things are static and we can look at it.
Okay.
So the method will be very similar.
Rama, just the Cantor-I picture one more time. Yeah. So here, those are homoclinic. I mean, that's a separatrix, right?
These are all separatrices, yes.
So there is another curve between those two, right?
Yes, yes. So there are these kind of heteroclinic orbit things and these are all the simple ones.
And between those two also there are other curves, right? I mean,
Yes. So between these two there are curves which go like this and here there'll be circles, yeah.
I didn't see.
So everywhere there are curves, only some representative ones are shown.
So the underlying sort of potential is evident from here.
Yeah.
Any more questions? Okay, if not the case, let's start with the speaker again. Move on to the next talk. Okay, the second speaker is Sarika Jaran, adaptation led. Tired? Sorry, the printing is not clear. Tired and cluster synchronization in hypergraphs.
That's Thunderbolt. That's not C.
That's not working. This will work.
No, it's